Good morning. I have the tough challenge to keep you awake in this first call after the social night last night. Let's see if I can succeed. I'm Luca. I'm from DigitalGlobe. At DigitalGlobe, we take very high-resolution satellite images of the Earth, like that one, which is Berlin, actually. I would like to start asking you to think for a second, how did you get here yesterday or today, for the matter? I'm sure pretty much most of you who didn't come with a taxi had a phone with a map on it. And perhaps some of you have even brought up the satellite view to understand more of the context of where we are. If there is a park nearby, you can go for a run later, where's the street, and if there's car parking, and so on. This is what I would like to talk about today, and I would like to talk about how satellite images are at the foundation of every map. To do so, I would like to tell you a story. Apologies if you've heard already. In fact, am I going to ask it? Have you ever seen this image before? Can you raise your hand if you have? One? Really? Two? Okay, pretty good. Well, actually, I love this story. This is the Great Survey of India. This story takes place 200 years ago. I hope it's cool to tell this story actually nowadays, but I think it is. British surveyor had mapped the whole of Britain, and now they wanted a bit of a higher challenge, so they thought to do the same in India. This is what they came up with, and they thought it was going to take them 5 to 6 years to do that. Well, it actually took them more than 60, and they lost hundreds of lives to diseases and I guess people aging as well at the time. Why did it take them so long? The reason being is because they put so much emphasis in accuracy. They already knew that the map needed to be very accurate to be meaningful. That survey ended up to be so accurate that through triangulation and calculations that I'm not going to bother you with, they managed to measure the curvature of the Earth, an arc of longitude. And therefore, they were able to prove Galileo's theory, although somebody still thinks otherwise, and I don't know whether that is real or not. But moving on, how did they do it? They started with a baseline of 7 miles, which they thought to measure with 100 chain foots. They took them 40 days to measure just that baseline because they did that measurement in so many different conditions, measuring temperature, humidity, and so on. They did it so well that it took them 40 days. Now, the story to me is already quite fascinating. Here's where it gets really, really cool. As they were doing the survey, they went up north, and they were close to the border, and they could see the Himalaya mountains. So I think they were really into this measuring thing, so they thought, let's measure the Himalaya mountains as well. Little problem is that the people from Nepal didn't let them in because they thought they were going to take over. So they thought to establish a number of observation points along the border. We're talking about 100 miles away or more from the actual mountain position, and they thought to measure the mountains from there. It took them 10 years. Needless to say, 2 years were just about calculations. And at the end, they measured the highest peak, which they named after one of the previous lead of that expedition, Sir Everest. And they got to that number there, 29,000 foot. If you are from the continent, as I am, that number means nothing to you. But it's important I tell the story this way because when they got to that number, they thought, well, nobody's going to believe that the mountain is exactly 29,000 foot. So what are we going to do? They sat together around the table, I suppose. I wish I could be there to see it. And they thought, okay, you know what? We're going to say a different story. We're going to say that the mountain is 29,000 foot plus 2. Really? They thought that number was more plausible. Fair enough. Now, today, with modern instrument and everything, we know that actually the Everest is 29,000 foot 29. So they were not far off if you think that they were doing that from such a distance. To me, this story is fascinating because as an engineer, the effort and the extent they went to get an accurate measurement, it's inspiring. But also it tells me that a map, they already understood 200 years ago that a map needed to be accurate to be meaningful. And the same belief we share in DigitalGlobe as we take high-resolution images of the Earth. Now, how does that translate? How accuracy concept translate into satellite images. Let me try to explain it to you. When you take a satellite images, each point on the satellite, on the image, doesn't necessarily match with the actual position on the Earth. That error is called the accuracy error and is measured statistically with a circular error and 90%. That means that if we take 100 measurements of that roundabout there, the center of that roundabout, the statue in there, could appear anywhere within a circle. If the circle is 100 meters, so if the accuracy is 100 meters, it means that that center can be anywhere within that circle, which is pretty poor, although that is the accuracy that some of the small sat should. CubeSat, they do slightly better. They do around 50 meters. Landsat is pretty good for what it is. It's 12 meters. Our satellite do much better than that. They shoot well within 5 meters. And that is really important when we look at mapping with a satellite image underneath. And I hope I can explain this with this series of pictures. This is, again, Berlin. And what I've done is, in a very trivial way, I've drawn a road vector, if you want. Yeah, no, I've used paint, so apologies, it doesn't look really cool, but it shows the purpose. So I've taken a picture that we had, overlaid the road layer, and then I've replaced that picture with a picture that we have got later, and later, and later, and later. And what you see is that even if we take new pictures, the overlap between the road vector and the picture itself, it's still really good over time, which is very important because that means that you can build your map and then keep updating the satellite picture, getting more fresh pictures every time, and you don't have to adjust everything again. So it shouldn't surprise at this point that our satellite images have been used in, and are used in most of the mapping apps that you do, use. So perhaps you haven't heard about DigitalGlobe before, but I'm pretty sure you've seen our pictures before. So accuracy is very important when we talk about mapping. There's another thing which is important, which is the way the map looks. From a satellite point of view, making a map that looks a satellite picture that looks good is challenging, especially when you operate a high resolution. High resolution here means 30 centimeters or 50 centimeters. This is what our satellites shoot. So the footprint on the ground is not extremely large. And as you take more images throughout the year, this is what you end up with. You end up with images that look slightly different in color because they have different seasonality. The atmospheric correction is slightly different because one day it's a bit more hazy, one day is less. That is all right, but it doesn't look too appealing from a user point of view. And we knew that, so we have put a lot of effort into making a mosaic where each pixel is balanced in color with the neighboring picture. So we have therefore created a country scale seamless mosaic, which we call Vivid, and that's how it looks. We've done that for many states in the world, actually. US is up next. Well, it's actually being produced at the moment, so it's going to be uploaded. China is next, and we have all of Europe, and we're going to refresh the content very soon. So where are we today? I mean, we have all this content. We have done this beautiful mosaic, and we have so many new players coming into the geospatial industry. And I'm not going to use big data, although I've just done it, so I had to reward it as data abundance. Hope you don't mind. But the point is, there's so much information, which to us at DigitalGlobe poses two challenges. The first one is delivering it. How do we empower developers, map makers, app makers to create beautiful apps using our content? To tackle that challenge, we have created our own Maps API. With Maps API, we provide two base map layers, which I will explain in a second, together with the OpenStreetMap road vectors and Mapbox terrain data. The two base maps you can choose from are the Vivid one, which I've explained, and the other one is a more up-to-date content, which is not necessarily mosaiced at a country scale level. With more up-to-date content, you can also have metadata, so you know when the satellite image has been taken, and that might be a useful and valuable information. The other challenge now, the data size. We have quite a lot of data. How much is that? We are around 70, well, our archive was a couple of years ago, more than 70 petabyte, and that's quite a big number. In fact, we want to overtake Facebook, so we're going to send a new satellite in orbit next year. We're really taking this seriously. So we have so much data into our archive. We've been in this sector for 15 years, and every year we are imaging the world at very high resolution. Guess how much power, how much information there is in those images that is not necessarily really exploited. How do we unlock that power? How we enable people to extract the information that they want over a time series, for example? We have created a platform which we are pretty proud about. It's called Geospatial Big Data, again, GBD. The concept of this platform is it's kind of simple. We put all our archive, everything we have ever taken, on the cloud. You can access the platform through APIs. You can access the archive, but also our image processing algorithm. These are things like atmospheric compensation, auto-rectification, car counting, road detection, building footprint extraction, any algorithm that we have done. In fact, you can also access our partners' algorithm, like Envy. Do you have your own algorithm for counting windows in a building? Very good. Package it, put it on the Geospatial Big Data platform, and you can use it for yourself, or you can even share it. You can share it with third parties, so if somebody else uses it, then we would recognize you some revenue for that. Do we have a gap in coverage in a certain place where you need a really up-to-date image? You send a drone, you take the image, you put it on the platform. You put everything on the cloud, and then you create a workflow to extract just what you really need, which is the information, okay? This, to us, is a fertile field. It's a fertile field for a developer to create new applications, to develop new products, to develop new answers to questions that we haven't thought about, because guess what? We don't have all the developers of the world, and we don't know all the possible use cases. We want to empower people to do that, and this is the right platform for that. I'll give you a quick few examples. With a satellite image, when you take a multispectral image, which we do, you can understand a lot about the territory that you're looking at. You can understand soil, different trees, man-made structure like concrete, asphalt parking, and so on. You can see water, so you can, for example, think of counting how many swimming pools there are in Berlin, if people dare having one. You can look at rooftop and look at the material on the rooftop. Do you want to know how many solar panels there are in Berlin? Well, I don't know, but I don't know. Is there sun here in Berlin at all? Okay, good. So there might be a few, but if you're interested to know the answer, Geospatial Big Data is the right platform to extract that information. You can create 3D model using stereo images, so images taken at a slightly different angle, not necessarily on the same day. That's called fortuitous stereo. And that is extremely high resolution because it's done with 50 centimeter or 30 centimeter images. So that is like a DTM, DSM, whatever, at an extremely high sampling rate. I love this example particularly. There is a company in the US who is looking at macroeconomic trends by just counting cars. Now, what they do is they count cars outside the manufacturing sites, and based on how that changes over time, and they do that at a scale over the whole world, they forecast the demand, the offer, the pricing, and so on. In fact, they've actually taken this a step forward, and now they're looking at retail stores. They can tell you if IKEA, or Lidl for the matter, is doing well by just counting how many cars there are out there, which is trivial to me, but nobody ever thought about it in DigitalGlobe. Now, imagine you are one of those retailer stores. Say you are IKEA, and you want to open a new branch in a place that you don't really know. How do you decide where to put it? Well, perhaps you want to do a bit of like geospatial analytics, geospatial understanding, intelligence, we can call it. Perhaps you want to look at a neighborhood and you want to see if it's wealthy or not. Perhaps it's important to you if the houses have a garden, how many cars they have in the driveway, what's the square footage of the house. Perhaps all of these information are important to profile your customer and the area. In fact, you want to do that at the whole scale of the village where you're looking at. And perhaps you want to see changes over time. Where are new stores opening? Which area of the city is booming? Which one is declining? You probably want to know all of that. Well, you can do that. So finally, you can take a decision which is a bit like data-driven and not necessarily a finger in the air. Another thing that the Geospatial Big Data empower you to use, it's something we are pretty proud of, is our crowdsourcing platform. That is called TomNode. It's an extremely simple website. I really invite anybody who's interested to contribute to the world causes to have a go at it. It just proposes you an image and says, is this a house? Yes or no. Is this a car? Yes or no. It's that simple. A 5-year-old person can use that. That crowdsourcing portal has been pretty famous for one of our most, I would say, interesting campaign, although it was not very successful. The search of the Malaysian flight, the MH370, I think. Well, there was a classic example of the needle in the haystack. We couldn't find the plane, of course. It was such a big place where we were looking at. But nevertheless, we had 8 million users trying to tag a number of satellite pictures. Some of those users are even famous, and some of them even thought they had found it. Well, Carney, I would think back about that. Anyway, how does the crowd help us? The crowd helps us a lot because it can improve our automatic algorithm and enhance the accuracy, can verify a lot of things, and can make things happen in a blink of an eye. And a mapping example is suitable for this context, I think. Despite most of the world as we know it has been mapped, there are many places that are not. And we understood that when we did a campaign in Africa trying to defeat polio. So there are people who are bringing vaccination to villages, but they don't know how much they need to bring. How do you solve that question? You look at a map, but what if a village is not on the map? And there are many like those. So this is a village in Guinea, that was pretty much not on the map. The cool thing is that when you reveal the satellite picture, you understand the truth, which is that is how big their village is. It's like 80,000 people that almost didn't exist from a mapping perspective. So we throw that image to a bunch of volunteers, and literally overnight, they mapped every footprint, every road of the village. They put the village on the map in a night time, which is a pretty good achievement if you think where we started. It took 60 plus years to map part of India, not even everything. And now, thanks to satellite images, we can do that extremely quickly with image processing algorithm, using the crowd, and so on. In fact, satellite pictures have empowered us to do even more. They've empowered us to understand the world we live in, to understand correlation between different places, to understand trends at a global scale. Okay? And this is not even 200 years old idea. It's more than 2,000 years old idea. And yet, I think we're just scratching the surface. Thank you very much.
Okay, maybe not. Okay, thanks, Luca, for the presentation. Really nice. Do we have some questions, maybe, regarding it? Nothing. Okay, cool. One question here.
Did you hear the question? Shall I repeat it? How does the last slide relate to OpenStreetMap? It relates in the sense that OpenStreetMap relies on volunteers. If you don't have volunteers in Africa, you're not going to map a village. And not necessarily you have the satellite pictures for every place. In this case, we had to go and take that shot because we didn't have that in our archive. And we used the volunteers in OpenStreetMap, I think, to map that place. So that's how, that's the link between that map and OpenStreetMap, I suppose. Does that answer your question? Okay. Okay.
There's one more.
Go for it. That's a very good question. Did you all hear that? That was pretty loud. How do we decide where to take the shot from the satellite? There's a number of parameters. It's an algorithm that uses information like cloud cover, for example. It doesn't make sense to take a shot over clouds. However, having said that, we have a pretty good, our satellite, which are fairly big, are 15 meters long. They have a pretty great accuracy, and they can point even in small places in between the cloud. That was the case in Nepal after the earthquake. The shot was pretty cloudy, but there was a hole just above Kathmandu, and we pointed the satellite there, and we managed to get a good shot. So cloud cover is one. Clearly, there are things like refresh programs that we have or customer demand. So based on where the satellite is passing and a number of parameters of how is the satellite going to be pointed, because really doesn't take any sense to take an image with, I don't know, 10 degrees off the horizon. We score places, and then we optimize the collection plan for the orbit. So the satellite passes on the Earth, talks to a central station that says, these are the places to take a shot for, takes a shot, send it to the central station. Within 2 hours, you have the image, pretty much.